I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video where we're talking about haloarenes. These are halogens on benzenes. They're called haloarene. Look right here. If I'm starting here with a halogenated benzene where the X represents a halogen atom, X can be here a chlorine or a bromine, and I were to halogenate this, either diatomic chlorine or diatomic bromine in the presence of a Lewis acid, and we don't have to be too specific over here, Lewis acid, a diatomic bromine, I will add one atom of a halogen onto this. I have three options. Here's my starting point right here, the halogenated benzene. I can add a halogen right here in the para position, I can add it in the ortho position, and I can add it in the meta position. The most likely aspect is that the ortho and the para positions will work, the meta position may not work. And the reason for that will be discussed in this video. Why is it that when you start here with the halogenated benzene, you add another halogen atom, it always goes into the ortho or the para positions, and the meta position is seemingly not seen? And let's look at that here in this video. You have to think about everything with regards to these 2 points. When you have a halogen on your benzene, the X being representing a chlorine or a bromine, you know that halogen can deactivate the ring by withdrawing electron density from that ring. Because you have a bunch of pi electrons involved in the benzene, the pi cloud above and below the plane of the benzene, it is pulled or sucked by the halogen present already on that benzene. It is inductively pulling the electron density, that halogen atom, and then deactivating the ring. But contrary and counteracting that fact is the second point. The halogen can donate electrons by resonance. Why? Look at your halogen like this. It's attached to some item over here. Here's your halogen. You have available, in terms of electrons, 6 electrons. 2 electrons are found right over here in the bond, but you have 6 electrons. 2 of these electrons can be donated relatively easy in terms of donation to the ring by means of resonance, and that can be a very significant positive factor which can lead to ortho and para directing of your haloarene. So let's look here at the resonance structures which are involved. Let's look over here at the resonance structure which would be seen when we have a meta attack. This right here is our representation. We're starting here with a halogenated benzene, a haloarene. It could be a chlorine, it could be a bromine. We're reacting it with diatomic chlorine in the presence of a Lewis acid. In a meta attack, what would be seen? You are looking at these structures develop. Here is my chlorine being attached to the benzene, and I'm generating over here a carbocation, which you would see everything else remains the same in terms of your double bonds. This right here is our first resonance structure. That's what it is. You know you have hydrogens here also, because benzene is a C6H6. I'm not showing you the hydrogens because it's irrelevant for this video. We have a meta attack. Now what we do is shuffle the electrons around. When we shuffle them around, we have another resonance structure which develops. And keep in mind, in all instances, your halogen group will always have those number of lone electrons around it. This is what it would look like. Here's my chlorine. We have a electron shuffling. The double bond comes here. The carbocation, which is your charge deficiency, is over here. And that's what we have. Now let's develop another resonance structure, and it would look exactly like this. You still maintain the chlorine here in the meta position. You have the double bond here, you have the double bond coming over here, and then you have your charge deficiency coming over here. You are seeing a shuffling around of this carbocation, and it's always either in an ortho or a para position when the halogen, your second halogen, attached in a meta position. What is the most significant aspect of this, or the disadvantage? It's the fact that these electrons did not come into play. Remember point number 2 I gave you at the very beginning? The halogen on a benzene ring can donate electrons by resonance. That effect is not seen at all in a meta attack. You only have 3 resonance structures which are seen, and the electron donation by means of resonance is not seen. That's bad. So this right here is the reason why you won't see a meta attack, because the most significant aspect is not seen. It does not come into play. When we're looking here at the ortho or the para attack, I'll show you only one of these, not the other, because it's the same either way. You'll see that you will have 4 resonance structures develop, and you'll have electron donation by resonance. That is, these electrons of the halogen will come into play for stability, and it will favor the ortho and para attack over the meta. When you have halogenated benzenes and you react another halogen, your ortho para are significantly more reactive than the meta. In terms of reactivity, reaction rates and all of that, the ortho para is significantly more favored than a meta. So you have to remember all of that. What we will do over here is show you a para attack. We won't show the ortho because the ortho and the para are exactly the same in terms of the resonance structures which are seen or the reasoning behind them. This is what would happen. You have a para attack, chlorine comes over here. You can picture your halogen to have those electrons around it. Chlorine is here, you know there's a hydrogen over here. We won't show it, but you know there is a hydrogen there. When I do it, I have a carbocation, a charge deficiency develop over here. Everything else is as is. Now what we can do is develop a second resonance structure. You'll have electron shuffling, and this is what it would look like. What you will see here is significant stability with regards to the interaction of the halogen, and it would stabilize everything much better than what you would have seen in the meta attack. This is what I have. My positive charge has come over here. You can see the carbocation is moving around. Now what we have a new resonance structure develop. Two of these electrons will come down and fill in this charge deficiency to develop a double bond between the halogen X and the benzene ring. To develop this resonance structure, just picture how the electrons are involving themselves. You will have two electrons developing this double bond, and you have your benzene ring, your double bond here, your chlorine over here in the para position. You have your 2 and 2, 4 electrons. You have a carbocation here. But in all of these other instances, for the meta and for this, except for this structure right here, you'll always notice there's a charge deficiency. The positive here represents a charge deficiency. Here you don't have a charge deficiency. You still have a complete octet even around the halogen. Think about it. You have 2 electrons, 2 electrons, 2 electrons here. Then you have this. You have 1, 2, 3, 4, 5, 6, 7, 8. An octet is complete. In all of these other instances, you don't have a complete octet. This right here is the most stable, even though you would think it isn't, but this right here is the most stable of the resonance structures. Everything else, there's always a charge deficiency, which means there's some sort of an incomplete octet. Consider this right here. You're looking at that point, you have a hydrogen over here, and you have that charge deficiency. When you're looking at this carbon over here, this carbon has 1, 2, 3, 4, 5, 6 attached here, attached here, attached here, and then there's a charge deficiency. It's an incomplete octet. Here you don't have an incomplete octet despite the charge deficiency. It's still a complete octet on the halogen. This again is the most favorable resonance structure. We can take it to the fourth resonance structure because I told you ortho and para will have 4, meta will have 3 resonance structures. In this specific instance, what you will see is a charge shuffling again, and you can go back to your representation such as this. Here's your chlorine. We started here with the positive here, positive here. You know the positive is going to come over here. You will have a charge movement such that you'll return back the 2 electrons to the halogen. You will have a carbocation charge deficiency over here, double bond here and double bond here, and that will complete your resonance structures. You have 4 versus 3 with meta. When you're looking here at the ortho or the para, you'll have 4 resonance structures, and the one which involves the electron donation by resonance by means of the halogen coming into play, its electrons coming into play, is the most stable with a complete octet around everything. Everything else will have 1 atom with an incomplete octet. That would be the carbon of your benzene. The ortho para significantly favored versus the meta simply because this structure shows up in the para, and a similar structure in the ortho where you could imagine that the halogen was in the ortho position, but you still have electron donation by resonance. Keep in mind, halogenated benzenes deactivate the ring by their inductive pulling of the pi electrons, but they also favor ortho and para by means of charge donation or electron donation through resonance. That's your message for this video. Thank you for watching.